All right, here's the video on 8.4 and 8.5. These are pretty quick. They're mostly calculator things that we're going to learn how to do, but we got to learn them as a concept. So if we're looking at this, basically 8.4 is all about inverses and then how you can use inverses to solve matrix equations. Then 8.5 is all about determinants, which is pretty much just a calculator operation that we're going to do. You can do it by hand, but we're not going to spend much time on that. All right, so first off, remember what the multiplicative inverse is in the real number system. So if we look down here, in the real numbers, the multiplicative inverse of a is 1 over a because a times 1 over a equals 1, and 1 over a times a equals 1. Right? If we multiply something by its inverse, we get back to 1. So the equivalent of 1 in matrices are called the identity matrix. So an identity matrix, here's a 2 by 2, here's a 3 by 3. But they're basically just got ones down the diagonal and then zeros everywhere else. They have to be square. It's not an identity matrix if it's not square, so you have to have the same number of rows and columns. All right, so the definition of the multiplicative inverse of a square matrix. Notice it has to be a square matrix in order to have an inverse. So if A is an n by n matrix, if there exists an n by n matrix A inverse, such that A times A inverse equals the identity matrix, and A inverse times A equals the identity matrix, then A inverse is the multiplicative inverse of A. A non-square matrix does not have a multiplicative inverse. So in order to be invertible, you have to have a square matrix. Not all square matrices have multiplicative inverse. If it does have one, it's said to be invertible. Kind of interesting spelling. It's invertible with an I, not A. And then or non-singular. If there is no inverse, it's said to be singular. All right, show that B is the multiplicative inverse of A. In order to do that, we're just going to take we're going to take A times B. So 5, 3, 2, 1 times -1, 3, 2, -5, and I should end up with the identity matrix. So 5 times -1 plus 3 times 2, that's -5 plus 6 gives me 1. 5 times 3 gets me 15, minus 15 gets me 0. 2 times -1 plus 2 gets me 0, and 2 times 3 plus 1 times -5 gets me 1. Now I need to do it both ways, so let's check the other way. So -1, 3, 2, -5, 5, 3, 2, 1. When I multiply these ones, again, the same thing should happen. So -1 times 5 plus 3 times 2 does give me 1. -1 times 3 plus 3 times 1 gets me 0. 2 times 5 minus 2 times 5 gets me 0. 2 times 3 minus 5 gets me 1. So indeed, they are inverses of each other. And notice B is A inverse, but you could also call A B inverse. So the inverse of the inverse gets me back to where I started. All right, so finding the multiplicative inverse of a matrix. Given A equals 5, 7, 2, 3, let A inverse equal WX, Y, Z. Find A inverse. So notice, if I'm looking at this, when I multiply, A times A inverse should equal 1, 0, 0, 1. So what that tells me is if I look at this, I'm going to have 5W plus 7Y. Then I'm going to have 5X plus 7Z. And then I'm going to have 2W plus 3Y. And then I'm going to have 2X plus 3Z. Let's just multiply them together. And now I know that has to equal 1, 0, 0, 1. So that tells me 5W plus 7Y has to equal 1. And 2W plus 3Y has to equal 0. And 5x plus 7z has to equal 0, and 2x plus 3z has to equal 1. All right, so let's solve the system of equations. So let's just multiply this guy, let's say by -5 and this guy by 2, add them together. So when I do that, the w's cancel, and I get 14 minus 15 gets me negative y, and then equals 2. So I get y equals negative 2. And from that, now let's plug it back in. I get 2w minus 6 equals 0, so I get w equals 3. And let's do the same thing here. Let's just do this one times 2, this one times negative 5. When I do that, the x's cancel, so I get 14z minus 15z, which gives me negative z. I get 2 times 0 equals negative 5, so z equals 5. And then plug it back in, I get 2x plus 15 equals 1. 2x equals negative 14, so I get x equals negative 7. So my answer ends up being A inverse equals, see here, w was 3, x was negative 7, y was negative 2, and z was equal to 5. Luckily, we're going to find a much better way of doing this. We don't have to solve a system of equations every time like this, but that's just one way you can kind of think about it and get to our answer. So, quick method. So this only works for a 2x2 matrix. If you're doing a 3x3 matrix or something like that, there's not really a real good quick way short of your calculator. But for a 2x2 matrix, the multiplicative inverse is pretty quick. So if we look at this little gray box here, the matrix A is invertible if and only if AD minus BC equals, well, look at this formula here. What can AD minus BC not equal? Well, it can't equal 0 because we can't divide by 0, right? So it's only invertible if AD minus BC is not equal to 0. If it does equal 0, then A does not have a multiplicative inverse. So let's use this formula. So we're going to multiply by 1 over AD minus BC. We swap the diagonal, right? A becomes D, D becomes A, and then we switch the signs on the other diagonal, right? So if I'm looking at this, I'm gonna do AD minus BC, which is equal to negative 50 minus a negative 54. So I get 4. Again, I just did 10 times negative 5 minus 9 times negative 6. So I get 4. So my A inverse is going to equal 1/4. And now I'm going to swap the 10 and the negative 5. I'm going to make the 9 and negative 6, I'm going to make them negative. So I end up with negative 5/4, negative 9/4, 3/2, and 5/2. Okay, so that's nice. That's the easiest way to get a matrix, inverse of a matrix, in my opinion. But one other way we could do it on our calculator, and this is kind of the standard way of how you do it for large order matrices. If I had like a 3x3 or a 4x4, I could use this method to get there. There's still even more ways that we won't talk about that we could use, but this is kind of the standard way you would do it. And so real quickly, I've already put it in my calculator here. So let's see here. Turn on my calculator. So I already put the matrix in here. So A looks like this 10, 9, 1, 0, negative 5, or negative 6, negative 5, 0, 1. And if I do RREF on that guy, notice what I get. Well, here let's make them in a fraction so I can see the whole thing. Notice what it spits out is this whole thing, 1, 0, 0, 1, negative 5/4, negative 9/4, 3/2, and 5/2. So notice that's what that's the answer it spit out there. And so notice what it ends up basically doing is the identity matrix that we attach to the end here. moves over to the left side, and whatever's left on the right side is our inverse. So if we had a 3 by 3, I'd append a 3 by 3 identity matrix on the end, do RRAF to it, and then I would end up with the same thing, identity matrix on my left side, and my inverse would be on my right side. So this guy right here ends up being my inverse. All right, so now the absolute easiest way for if we're allowed our calculators, which for 3 by 3s I'm not going to make you do it by hand or anything, is if we just punch in a calculator here, punch in our matrix. So I already did this here. You can see the matrix B, 1, 0, 2, negative 1, 2, 3, 1, negative 1, 0. I can just go in and say, oh, let's do matrix B, and then I'm just going to hit the X inverse button here, and there we go. So 3, negative 2, 4, 3, negative 2, negative 5, and negative 1, 1, 2. And that's probably the easiest way right there. So, and we can double check if we wanted to go in here and do matrix. Let's do B, and let's do it times B inverse. Notice we get the identity matrix. So indeed, it does work out. All right, so now matrices can be used in a lot of different ways. One of the ways you can do it is to set it up a system of equations. Instead of using an augmented matrix, you can use a matrix equation. So instead of just writing A1, B1, C1, D1, etc. in our augmented matrix, we could write it in this form right here. Because notice what ends up happening is I take my row and dot it with my column. So when I multiply that first row there, I end up with A1 times X plus B1 times Y plus C1 times Z equals D1. So here's another example. Here it's I have 1x, 0y, 2z equals 6. So 1, 0, 2, and then negative 1, 2, 3, 1, negative 1, 0, negative 1, 2, 3, 1, negative 1, 0. And so when I multiply those out, I should get 6, negative 5, 6. So this is just another way of solving systems of equations. It does have some benefits. Sometimes it's very handy to know this way. So let me just do an example here. So if AX equals B, what I can do is I can multiply both sides by A inverse. So if AX equals B, I'm going to multiply both sides by A inverse. Now when I do that, I didn't give myself enough space. If I multiply the left side of the equation by A inverse, I have to multiply the left side of the right side of the equation by A inverse. I cannot just do BA inverse like that, because remember, matrix multiplication does not commute. So I cannot do BA inverse like that. Now A inverse times A is just the identity matrix, and then the identity matrix times X is just X. So I get X equals A inverse B. So if AX equals B has a unique solution, then X equals A inverse B. So the short answer is multiply on the left by A inverse, and we've got our answer. So system of equations here, we can just write it out here. Notice we could rewrite this as 1, 0, 2, negative 1, 2, 3, 1, negative 1, 0, and then we have X, Y, Z, and then it equals 6, negative 5, 6. So if I want to solve this, what I'm going to do is I'm going to multiply by, if we call this matrix A, we're going to multiply both sides on the left. We have to do it on the same side, so I'm going to do it on the left by A inverse. So notice if I do A inverse times A, I'm going to end up with just the identity matrix. So I end up on the left side, I just get X, Y, Z equals, because the identity matrix times anything is just itself. And then on the right side, well, let's just go ahead and write it out. So I have 3, negative 2, negative 4, 3, negative 2, negative 5, and negative 1, 1, 2. And I'm going to multiply that times 6, negative 5, 6. So when I do that, I end up with 3 times 6 is 18, plus 10, and then minus 24. And then on the next one, I get 18 plus 10 minus 30. On the next one, I get negative 6 minus 5 plus 12. So my answer ends up being 28 minus 24 is 4, 28 minus 30 is negative 2, and 1. So I end up with that as my answer. So that's what x, y, z is equal to. X is 4, y is negative 2, z is 1. If we wanted to, we could check it on our calculator. Now I already put in an extra matrix C, which is just that 6, negative 5, 6. And I called this matrix that I called A here, in my calculator I called it B. So I'm going to do B inverse times C. So B inverse times C. And notice I get 4, negative 2, 1 as my answer. Pretty nifty. All right. Finally, some simple way of encoding messages is you can use a matrix to do that. So if we want to, basically we're going to take our letters and we're going to list them as columns in order. So like B-A-S-E, we're going to write that as B, B-A-S-E, and we're going to convert those letters to numbers. So we fill up our columns first. And if we don't have a square matrix, what we're going to have to do is we're going to have to add zeros to make it into a square matrix. So if we look at the word base, that's going to be 2, 1, 19, 5. And then if we want to use the matrix 5, 7, 2, 3 to encode, we're just going to multiply 5, 7, 2, 3. And when I do that, I'm going to get 5 times 2 plus 7 times 1 gets me 17. 5 times 19 plus 7 times 5. So that's 95 plus 35 is 130. 2 times 2 plus 3 times 1 is 7. 2 times 19 is 38. Plus 15 gets me 53. Make that 7 a little bit clearer. So that would be the word base encoded. And so now if I wanted to decode it, it's as simple as taking the inverse matrix here. So if I look at, let's find out what the inverse matrix of 5, 7, 2, 3 is. So again, if we look at the determinant, or sorry, not determinant, well, that's what it is, but we haven't learned that yet. If we look at it, it's going to be 1 over AD minus BC, so 1 over 15 minus 14. We're going to swap A and D and make B and C negative. So I get, well, that's just 3, negative 7, negative 2, 5. Now I'm going to take, so this is my inverse matrix right here. And I take my inverse times my coded matrix. And notice 3 times 17, that's 51, minus 49, that gets me 2. And then 3 times 130 is 390. Or sorry, 390 minus 7 times 53, which is, what, 371. So that gets me 19. And then negative 2 times 17 is negative 34, plus 5 times 7, well, that's just going to be 1. And then negative 260 plus 265 gives me 5. And I get back to where I started. And that's it for 8.4. Realistically, know how to do the stuff on the calculator and know the 2x2, this little formula right here for the inverse of a 2x2 matrix. I'm not going to make you do the REF version or anything like that. I'm not going to make you solve a system of equations. Realistically, just understand what the inverse is and how to find it using your calculator. If you understand that, like in this idea right here where we multiply on the left side by the inverse to get the identity matrix, then you're in good shape. All right, 8.5, determinants. So these bars represent the determinant of a matrix. For a 2x2 matrix, it's very easy. Do you remember in 8.4 how we multiply by 1 over AD minus BC? This denominator here is actually the determinant. So the determinant is just AD minus BC. So in this one, it's going to be 10 times 5 is 50, minus 9 times 6, which is 54, so I get negative 4. This one I get negative 15 plus a 32 because it's a negative, so minus the negative 32, so I get 17. And then 6 times 2 is 12, minus 12, and that equals 0. And so remember, if that equaled 0, this means this matrix would not have an inverse. It would be not invertible. All right, so how can we do that example using a calculator? So again, let's just punch in our matrix. It's a 2 by 2, and it's 10, 9, 6, 5. And then I'm just going to go into matrix, math, det. I'm going to do it in my matrix. I called it D, and I get negative 4. So similarly, I can do that. There is a way to do it by hand. I'm not too concerned about it. So just know that you can if you wanted to, but we're not gonna spend time on that. So if I just make a new matrix 3 by 3, 4, 1, 0, negative 9, 3, 4, negative 3, 8, 1. Then I'm going to go ahead and do math determinant on E. This ends up being negative 119. And you can go even larger. You can do, so last one, I know it's kind of tedious to watch me plug this in. Maybe I should have done it ahead of time, but let's do 6F. This is a 4 by 4. Now this, like 3 by 3s are not too bad to do by hand. Anything beyond that and they become a real pain. This would not be fun to do by hand. You can just take my word for it. I said 0. Negative 1, 1, 0, 2, 0, 2, 0, negative 3, 2, 3, negative 4, 1. So, luckily for our calculator, it's no big deal. Let's do det. I get negative 79. Hopefully I didn't do a typo there. All right, so that is the end of chapter 8. And the next section that we're going to start talking about is on conic sections. So I'll see you then.